particles, matter and antimatter, we can ask ourselves the question, what would you do if you had something that was made of matter and you turned all of the particles in that matter into antiparticles? Would nature use that new system consisting of antiparticles? Would we expect to see that reproduced in nature? That idea of turning particles into antiparticles goes by a fancy name of charge conjugation. You needn't worry about the technical name. It basically means if you had an electron, turn it into a positron. If you had one of the protons in your body, which we view very simplistically as made of quarks, turn those into their corresponding antiquarks. Because what I failed to tell you is that not only does the concept that Dirac introduced, that the electron has an antipartner, all of those other matter particles in our little periodic table of the fundamental building blocks also we would expect to have antiparticle partners. And indeed we find them in nature, in our experiments. Protons we think of looking like that, and antiprotons. Some matter particles are made up of protons and antiprotons, of quarks and antiquarks, bound together in a little system, bound together by these gluons. I'm just giving you an example here of a particle called a neutral kaon, which would turn into its antiparticle if you did this swapping of the matter particles with their antimatter counterparts. I use this example because they're going to turn up in a few minutes. Okay, that's called charge conjugation. Parity charge conjugation. Do the laws of physics respect these operations? People thought they did until the 1950s. And this was a real revolution in our understanding of nature. A couple of physicists, Chinese physicists, realised that nobody had really put this to the test. Is there a symmetry between our world and what we see in a mirror? So they pointed this out, and then some experimenters set to work to see whether nature was indeed symmetric under this mirror reflection. The experiment was rather complicated, but let's try and sketch what they found, the experimenters. What they did, they took a particular radioactive nucleus. It was a cobalt-60 nucleus. And they stuck these nuclei in a magnetic field. What happens when you stick these nuclei in a magnetic field? You can actually imagine the nuclei all lining up in a particular direction, and for our purposes, you could think of them spinning around in a certain direction. And the way that they spin depends on the direction of the magnetic field in which they find themselves. Being radioactive, these nuclei decay away and they spit out electrons, which in those days also went by the name of beta rays. And so the experimenters asked themselves the following question. Here is the cobalt nuclei which I've got spinning in a certain way in my laboratory, spitting out electrons. What would that look like if I looked at it in the mirror? If I looked at it in the mirror, the cobalt nucleus would look as though it was spinning in the other way. Okay, spinning in the other sense. You'd sort of have this. And then they asked themselves, now where are the electrons that these guys are spitting out going? And they got an interesting result. The electrons were all preferring to go, if the cobalt nucleus is spinning this way, the electrons preferred to go that way, down, rather than go that way up. That doesn't sound like such a big deal until you realise that that means that in nature we would never see this situation. We would never see the situation where the electrons were going down and the cobalt nucleus was spinning the other way. Nature doesn't seem to use that configuration. Parity this mirror reflection appears to be not respected by nature. The only way it would be symmetric would basically be if the same number of electrons were going that way as were going that way, and then I wouldn't be able to tell whether I was in the mirror world or not. So this really rocked physics because they couldn't explain this. They had to think about it some more. The force which is responsible for those cobalt nuclei falling apart is the weak force. So after scratching their heads, people realised the weak force does not respect this mirror reflection. There is some sort of left and right-handedness in nature that matters. Okay? It seems that the other two forces that people were studying, the strong and the electromagnetic, did respect this mirror reflection. Physicists, however, they're quite resourceful sort of characters, and they said, all right, when the dust settled and they got over it, they said, okay, well, look, parity is not respected by nature, but we're sure that if we were to look in the mirror and at the same time turn all our particles into antiparticles, we'd see something which nature would use. That the combined operation of looking in a mirror and turning the particles into antiparticles would be respected by the laws of nature. So they would have figured that out probably sometime in 1956 or 1957, and all was sort of well again. Except that the experimenters were still working. This is just an example of what we would mean by taking a system, looking at it in the mirror and turning all the particles into antiparticles. For example, if you had an atom of hydrogen with a proton and an electron, and you looked in the mirror, did the parity, that's doing the parity, and you changed the proton into an antiproton and the electron into a positron, that would be an anti-hydrogen atom. So CP is doing both the charge conjugation and the parity. This is an example from CERN of the death of an anti-hydrogen atom. CERN is actually able to make, only a few of them, anti-hydrogen atoms. Who has seen Angels and Demons? Some of you. I had to put my hand down. I actually haven't seen it yet. But the premise of that film was that somebody who has seen it could fill us in better. Somebody steals antimatter, e.g. anti-hydrogen, from CERN. So the basic premise of Angels and Demons was correct. CERN can make antimatter. It can make anti-hydrogen atoms. They are as real as hydrogen atoms. And the interest now is whether they really behave the same way. The problem with Angels and Demons, I'll just point out, is that in order to have made the gram, I think it was, of antimatter that was stolen from CERN, CERN would have to run its present accelerators and so on for 1 billion years to make that much antimatter. So don't worry. Don't worry. But the point is that you can make a system in nature that looks like the combined operation of this, and it seems to be a valid thing that nature uses. So CP, the combined operation, our laws of physics seem to respect that symmetry.